So I will begin with now. My title of the talk is Ultra Precision Machining and Enabling Technology for Nanometric Surface Finish. Is slides changing?
No, madam.
Okay,
First slide we can see it, madam.
Just a minute. Is it changing now?
Yeah, changing, madam.
Okay, quickly I will introduce myself first of all. I am working at CSIO as a senior scientist in Department of Optical Devices and System Division. I joined CSIO as a scientist in year 2012, and before that I was working as a quick hire scientist fellow. My field of specialization is optomechanical instrumentation, and my broad research domains are optical system design and fabrication of optics modules for soft X-rays, infrared optical element, and further molecular dynamic simulation based modeling, ultra precision machining of optics, improving the figure and the finish accuracies in the nanometric range, optical metrology, smart materials, and precision engineering. These are my broad research domains. And I'm also working here as an assistant professor in Academy of Scientific and Innovative Research, which is an academy of CSIR, teaching postgraduate and doctoral academic activities. And further, I'm also associated as a faculty member in Indo-Swiss Training Center, giving hands-on session to the diploma courses. Is there any problem in the screen, sir?
No, madam. Some of the persons are drawing something, I think so.
Okay,
Yeah,
no issues.
I cleared it.
So briefly, to begin with it, I will introduce about what CSIR is about. Many people may not be aware of CSIR itself. So CSIR is a Council of Scientific and Industrial Research. Having a pan-India presence, the CSIR, it has a dynamic network of 39 national laboratories with 37 outreach centers and innovation complexes. So it consists of a networks of lab under various domains like engineering sciences, information sciences, physical sciences, chemical sciences, and biological sciences. And CSIR R&D expertise and experience is it comprises of around 3,500 active scientists supported by 8,000 scientific and the technical staff. It covers a wide spectrum of science and technologies ranging from radio and space physics to nanotechnology, biotechnology, aeronautics, instrumentation, environmental engineering, information technology. So it covers almost all the areas of science. The brief introduction about CSIO, that is Central Scientific Instrument Organization. The mandate of my institute is basically research, design and development of scientific and industrial instruments for societal, strategic and high science application. The core strength of this institute are basically opto-avionics, that is developing of optic instrumentation for avionics components, holographic, aspheric, freeform and diffractive optics, and photonics, sensor actuator and computational instrumentation, seismic instrumentation, biomedical and agro instrumentation. We also have the MTech as well as the PhD program under ACSIR, which is Academy of Scientific and Innovative Research, which provides full-fledged MTech as well as PhD degree for various engineering as well as physical sciences domain. So the key areas and the technologies of CSIR, CSIO in the recent times are, recently we have been associated or developed various instrumentation technologies for sustainable agriculture as well as for aviation sector, technologies for smart cities, technologies for healthcare. So quickly I will go through the various technologies which are developed in the recent past by CSIR, CSIO. Like instrumentation for sustainable agriculture, we have developed tractor mounted soil variability mappers, pesticide spray nozzle device, and e-nose multigrain moisture analyzer, as well as tea manufacturing machines. Further, we have a dedicated team of scientists working for instrumentation for healthcare also. So we have various technologies developed for the healthcare domain, like exoskeleton devices, myoelectric arm, head gesture manual wheelchair, customized implant depending upon the requirement of the patient or the doctors, postural stability analysis, design and development of low vision aid for visually impaired, and one of the latest is the Divinan, which is a blind reader machine for the blind persons, which can read language in almost 7 to 8 languages. Further, in instrumentation for healthcare, we have developed linear accelerator, which is installed also at Mumbai, and portal imaging device, cephalogram, and laser lithotripsy system. We are also into the instrumentation for smart city, like early detection of earthquake for the Delhi metro, and recovery of the very high cost MOF products from the waste batteries. We are also working on the recycling of the waste CFL, water quality monitoring, as well as electrical energy parameters monitoring. The main area of CSIO is basically optics instrumentation. So we extensively work for the instrumentation for Navy as well as the military aviation at CSIO. So these are our flagship projects in which we are associated with it right now, like scan laser 3 see-through displays, AMLCD see-through displays for fighter aircraft as well as for Air Force as well as for Navy, and military aviation display test platforms, and various components, optical components associated with these displays, like optical thin film coated lens, beam combiners, aspherics freeform lenses for these display systems. This is head-up display. We are also associated with the various other parts of the aircraft, like aircraft exterior as well as the ship deck lighting. We are into design and development of the drogue as well as the probe lights for aircraft for refueling into the air, anti-collision lights for the aircraft, and LED based NVG compatible fin as well as wing navigation light, and taxi as well as the landing light. I will be discussing about few in my coming slides. So another major domain is the precision machining we are associated with. We can machine almost all kinds of metals, glass and plastics, and can generate all kinds of shapes, whether it is flat, window, spherical, aspherics and freeform, or any ruggedized assembly required for any optical instrumentation. So we work for the different areas like infrared optics, strategic application, aviation and space optics, ophthalmics like development of intraocular lenses, contact lenses, mold inserts, etc. We are also into the coating techniques, different kinds of coating facilities we are equipped with to develop flat or uniform or a graded index response. So we can develop or we are developing different kinds of interference filters like anti-reflective, band pass, band reject, neutral density filter, notch filters, Rugate filters for different strategic as well as the societal applications. So the main area in which I am associated with it is basically the optical instrumentation. Now, as we are all aware of the very basic optical instrumentation like microscope, telescope, cameras, spectacles, binoculars, contact lenses, film projector, and the human eye, which is also the best example of the optical instrument. So what if we think about what they have got in common is the lens. So all these optical instruments, they comprises of a lens, which can be a plano-convex, biconcave, plano-concave, or it can be of any shape. So lens is the most critical part of any optical instrument. So there are various challenges associated with the fabrication of the lenses, like conventional conventional lenses are normally spherical or flat in shape. So, so for making this lenses, conventional lenses, there is certain fabrication process involved. So the basic process is comprises of these five steps, that is slitting, trepanning, grinding, followed by polishing and then coating. So conventional lenses means which are of very normal in shape, which are not of intricate shapes, not complex shapes, and which are used in the conventional optical systems. Like it can be a flat or spherical. So first is the slitting. Slitting basically refers to cutting of the glass material into a manageable sizes. The very bulk or large pieces of glass, they are converted into the required shapes and sizes by the process known as the slitting. It is basically done with the two kinds of tools, like it can be a diamond tipped glass cutter tool, which is used for cutting very small and thin glass sheets, or it can be done with the help of a diamond wheel, which is used for very thick and large glass sheets. So this is a diamond tipped glass cutter tool, which is normally used for cutting very thin glass sheets. So this process is known as slitting, and whereas these are the grinding wheel which are used for the these are the wheels, diamond wheels, which are used for the slitting of very large as well as the bulk glass. So this can be done either by slicing, that is longitudinal cut for a longer pieces, or it can be done by dicing, that is the horizontal cut for square or near square pieces. Now, after slitting, the process is called the trepanning. That is, all the lenses, they are made of certain, they are of required diameter or or the size. So trepanning basically refers to the cutting of the glass blanks into the circular shape for further processing. So different sizes of trepanning tools are available for various size of the lenses. So converting of the glass blanks into the circular shape is basically the trepanning process. Trepanning is further followed by the grinding. Grinding is basically nothing but it's the selective removal of the material from the trepanned component to generate the required radius of curvature. As we all are aware that lens is nothing but to focus the beam to get a magnified image, or to focus the beam at a particular point for any application. Basically the role of the lens is to focus the beam or to magnify the beam. So it any lens comprises of the radius of curvature. So this radius of curvature is normally generated by the grinding process, which is the selective removal of the material. As we can see, this is the trepanned glass component, and these are the grinded with desired radius of curvature. This radius of curvature changes depending upon the application. So this is basically the grinding process in which the different components, they are mounted by the pitch into a blank, which is normally known as the grinding tool, and they are the material removal is done by the use of the abrasives of the particular or required sizes, and material is removed in a very controlled way. Now, after grinding, the final mechanism or the final process is the polishing. Because the lens cannot be used if it is opaque, so it has to be very clearer and transparent. To make the grinded lens transparent, a polishing is the process which is used. Polishing is very similar to grinding, but there's a difference in the size of the abrasive, and the material removal rate is very low as compared to the grinding. So we can see here, this is the grinded lens, which is opaque, not transparent. After polishing, we get a very transparent lens, which can be used for any magnification or focusing. The final part of any lens fabrication is the coating. So the polished lens has to be coated with a suitable material, basically to increase the transmission of the lens. So coating is the final stage, and it is basically done to make the lens scratch resistance. It is also done to selectively filter the light passing through it as well as to attenuate the light uniformly. So any optical instrument, if it comprises of any lens, then it coating is the final and it is the required step which has to be performed. So these are the basic steps which are involved in the fabrication of conventional lenses which are used in the conventional optical instruments. So as we are if we ask in the present scenario, the optical instruments are used in almost in the entire electromagnetic spectrum. So I've been associated with the precision, development of precision components which are used for optical instruments ranging for the different wavelengths of the electromagnetic spectrums from X-rays to visible and to IR. So for X-rays, I have been involved in the development of silicon mirrors for synchrotron beamline. For visible, aspheric lenses for low vision aid, plastic lenses for see-through displays, taxi and landing reflectors for aircraft, and for infrared region, I'm associated with the development of diffractive optical components for thermal cameras, precision lenses for hotspot detection for infrared microscopy, and development of India laser rod for beam steering optics, and precision component for IRST, that is infrared search and track. So for the development of the optical components for the different wavelengths, they are not the conventional optics. So they are the like advanced optics which are not which are very complex in shapes and cannot be fabricated by the conventional methods. So here what ultra precision machining comes. Ultra precision machining is basically kind of nano machining which is used to generate very complex shapes of the optics which are used for the present optical instrumentation. So as we know that that deterministic high precision methods and finishing methods, they are the need of the present manufacturing scenario. So the need of ultra precision is basically to improve the interchangeability of the components, to improve the quality control, to produce the components with a very improved roughness as well as the reliability, and also to enhance their fatigue life. So according to the Taniguchi, the machining process, they were classified into three categories. Normal machining, in which the machining accuracy achieved is up to 1 micron, and precision machining is that in which the machining accuracy is up to 0.01 micron, that is up to 10 nanometers, and ultra precision machining is the process in which the machining accuracy is achieved up to 0.001 micron, that is up to 1 nanometers. That means we are talking in terms of the surface quality in terms of nanometers. So ultra precision machining is also known as the nano machining. So it has various applications like ophthalmics. If you talk about intraocular lenses, contact lenses, mold insert, corneal implants, all these are made by ultra precision machining because of the surface quality requirements. Electro-optics like thermal imaging, consumer electronics, these are another area of application of ultra precision machining. The precision mechanical components like biomedical implants, aerospace components, automobile components, all these comes under the category of ultra precision machining. Now for the examination of very high resolution images, different kinds of mirrors are used for focusing and for acquiring the images. Like if we talk about instruments like TEM, they all require precision components. So these are made by some ultra precision or nano machining processes. So broadly, the ultra precision machining processes are classified as diamond machining and ultra precision grinding. Diamond machining can be of various types, like it can be of face turning, it can be of fly cutting, it can be a diamond micro chiseling, It can be fast tool servo turning for making the lenselet arrays. It can be a slow tool slide turning, which is used for making the off-axis mirrors for various applications. And another class of category is the ultra precision grinding. The difference between diamond machining and ultra precision grinding is that diamond machining is a single point cutting, whereas grinding is a multi-point cutting. So always a single point cutting gives a better accuracy than the multi-point cutting. So single point diamond turning is the most advanced technique of the ultra precision machining, and we at CSIO have this facility. So I will be discussing about single point diamond turning and for what application optical instrumentation it can be used. Single point diamond turning is nothing but it is a ultra precision machining which uses a single point diamond tool. As you can see here, it consists of a tool which has a natural diamond, and with the help of this we can generate any complex geometry which are difficult to do by any conventional methods, and we can achieve very high accuracy as well as the repeatability, and can produce mirror finish, that is we are talking of surface quality of less than 10 nanometers, and we can produce any kinds of shape, whether it is a flat window, spherical, aspheric, freeform, or any shape, any kind of conic section or any freeform shape. And the disadvantage associated with the grinding is that it cannot be used for soft as well as ductile materials. So single point diamond turning can finish soft ductile materials which are very difficult to polish. So different kinds of optics can be generated or manufactured by diamond turning process, like freeform surfaces, hybrid optics, and microstructured optics. Now, diamond turning is a process through which we can machine different class of materials. Like we can machine different types of metals like aluminum and its alloy, OFSC copper, which is basically oxygen-free high-conducting copper, beryllium copper, brass, electroless nickel. These kinds of metals, they are used for different applications. Polymers can also be directly machined by diamond turning. I will be discussing in my next slides, like acrylic, polycarbonate, polystyrene, and single crystal material, which are very difficult to machine but have wide application in electronics and optics, like silicon, germanium, zinc sulfide, zinc selenide, can be machined with diamond turning. Now, the diamond turning is associated with different types of process parameters which can be classified as controllable as well as the uncontrollable parameters. Controllable parameters are those which are in the hands of operators, like all the machining parameters like tool feed rate, depth of cut, spindle speed. This we can control and select as per as our requirement. But there are certain uncontrollable parameters like which are not in the hands of operators, which arises due to the uncertain machining conditions, like vibration, material swelling. Suppose I am machining plastic, so there is some certain swelling effect. Like after machining, the material swells, then it cools down and comes back to a different shape. So all these are the uncontrollable parameters. So these all parameters leads to the certain sources of error which are not required in any nanometric application, in any optical instrumentation. So we extensively work or do very good research on this, how to eliminate these kinds of error and to achieve a very good level of optics which can be used for different kinds of optical instrumentation. So I will be discussing 1 and 2 parameters, that how we have controlled them and how this optimization has led to the fabrication of different optical elements. So as I told that diamond turning is a skill dependent process. So it definitely requires an adequate understanding of various factors which decides the outcome. So if I talk about machining parameters, so the surface quality depends upon the selection of the input parameters, like proper combination of process parameters should be there, like tool feed rate, spindle speed, nose radius of the tool, and depth of cut. Now, if we talk about vibration, so signatures of vibration is present in almost all the machining process. So it any machining process, whether it is of nanometric level of accuracy, also the vibration signatures, they are present. So our main aim is to minimize these signatures of vibrations. So in case of diamond turning, the vibration of a tool depends on its extension from the tool holder, which we commonly say as tool overhang. So to optimize this effect of tool workpiece vibration, we have performed a series of experiments by varying the overhang from 8 mm to 27 mm depending upon the tool holder geometry as well as the logistics. So as it can be seen that when we vary the overhang from 8 mm to 14 mm, the surface roughness is basically improves, like it's reducing. So surface quality is improving. And when the overhang increases from 14 to 27, the roughness started increasing. So we found that the surface quality is optimum at 14 mm overhang, and this can further be seen by the power spectral density, that is the frequency spectrum obtained at different overhang. This is at 8 mm, this is at 14 mm, and this is as 27 mm. So we can see that very less frequency, random frequencies are present at 14 mm, which leads to an optimum surface quality in comparison with the 8 mm as well as 27 mm. So this is one of the most important parameters through which we can optimize the or reduce the effect of vibration in any optical component. Now, another very important parameter associated with the diamond turning is the tool wear. It not only affects the surface finish, but it affects the profile. Suppose I want to achieve a radius of a certain dimension. So if the tool wear is occurring, then we are not able to achieve the radius accurately, as well as surface finish is also deteriorating. So we have studied extensive study how to study the effect of tool wear on surface roughness by performing a series of machining operation on silicon substrates, and we divided the machining into different fixed time intervals, and after each time intervals the diamond tool was inspected for the tool wear and the workpiece we inspected for the surface finish as well as the profile accuracies. So these are the images of the diamond tool. This is an image of a new diamond tool, which is a unused tool. Then after 50 cycles, after 100 cycles, 150 cycles, 200 cycles, and 250 cycles, we could determine what is the life of the tool and at what time we should stop machining with that tool so that it should not affect the optical components which we are fabricating. So we lead to a very significant results which have been used for the fabrication of optics further. Another two more important parameters, these are also uncontrollable parameters. Dynamic balancing, it plays a very important role in maintaining a good profile as well as the surface finish. So if the machine mass is not balanced and it has certain amount of eccentricity from the center rotation, then it leads to certain unbalanced forces, unbalanced centrifugal forces, which further leads to the vibration. So we did some experiments, and this can be seen that due to the presence of the unbalanced condition, the vibration generation of vibration takes place and it deteriorates the surface roughness as well as the profile accuracy. And effect of chip extraction is also very important to maintain the proper condition around the cutting zone. So the chips has to be properly collected, otherwise it will lead to the formation of certain unwelcome scratches on the optics which we are fabricating. So we have optimized all these parameters for the different class of materials which are used for various applications, and we could come out with the various optics which is now being used at various platforms. So I will be discussing some of the optics which we have fabricated and now being used at various platforms. First is the diamond turning of aluminum reflectors. Now, we have designed as well as developed the LED based taxi as well as the landing lights for LCA aircraft Mark II. Now, as we see that in the ground-based astronomy, aluminium 6061, that is a military grade aluminium, it is the most often preferred material because it has very good thermal properties and very high specific stiffness, which is required for the aerospace application, and it is low cost in so that is also the reason why it is preferred. So, aircraft normally requires two kinds of light for taxiing and landing, out of which one is installed in the port side of the nose undercarriage, and the two others are installed on the starboard sides. So, all aircrafts which are intended, I'm talking about the fighter aircrafts only, all aircrafts intended for night flying, they are equipped with taxi as well as the landing light. The purpose of the taxi as well as the landing light is basically to eliminate the forward zone in the front of the aircraft during taxi and landing. So we have replaced the conventional reflectors with the aluminum reflectors, which are parabolic in shape. These are designed and developed at CSIO. So and these are made by diamond turning process. The speciality of these reflectors is that they are parabolic in shape, and we have replaced the traditional bulbs with the LED lights in the taxi and landing systems. So it leads to the improved enhanced brightness, and it consumes less power by a factor of 7 to 8, and therefore due to the consumption of less power there is a less consumption of the fuel as well as the cost. So these are now 10 units of taxi and landing lights. They are installed in LCA light combat aircraft. They are tested and now they are installed. So further, I'm also associated with the diamond turning of plastics for see-through displays. Now, initially, all the see-through displays, they comprises of the glass optics. But nowadays, the optical grade plastic, it is replacing the glass optics because of the very high refractive index, low cost, low specific mass, and high impact resistance. So the use of polymers in optics, it provides a very good flexibility to designer as well as the manufacturer. So this is basically a head-up display, which I'm saying as a see-through displays, which is designed and developed by CSIO. So head-up display basically it eases the workload of the pilot by displaying the all the flight information or weapon information or any other information associated with it in the windshield of the aircraft, and like pilot at the same time is able to see all the symbology on the screen and also able to see the outside world. So it basically focuses the outside world as well as all the symbology in the infinity. So this focusing is done with the help of the optics. So we have tried to replace the glass optics with the plastic aspheric optics, which is designed and developed by my group by ultra precision diamond turning. So the greatest advantage of replacing the glass optics with the plastic is that there's as we are moving from spherical to aspheric, then definitely there is a reduction in distortion and abrasion, and there is a reduction in the weight by 30%. So this was the major achievement in this work. And further, we are also designing and developing the aspheric lens for visually impaired persons. As we know that visual acuity normally refers to the clarity of the vision, and visual impairment is one of the major health concerns all over the world. Those who are nearly blind, they are associated with the different problems, like there is a central field loss, that is inability to recognize any object or face, peripheral field loss, which leads to difficulty in mobility or navigation, or it can also lead to an overall blur. That means there is a blurred vision due to reduced contrast. So we have developed a precision manufacturing protocol for the fabrication of plastic lenses, which can be used as a low vision aid for the nearly blind person. The drawback with the existing system was that they use the spherical glass magnifier of very high diopter. They causes the distortion at the periphery and which reduces the field of the vision. So if such type of magnifiers, if they were corrected for distortion, it leads to multi-element in nature, and since they were made up of glass and sphericals, so the entire system become quite heavier and it cannot be wear for a longer time. So what we did is that we replaced the spherical with the aspheric lenses and glass with the plastic lenses. So it's led to basically low fatigue factor due to the reduced weight, improved performance because of the less distortion, and low cost because of replacing the glass with the plastics. So we compared the performance by studying the defocusing effect of on the point spread function for a peak to valley for spherical and glass spherical as well as aspheric lenses. So it was found that the defocusing effect for the aspheric lenses reduced comparatively, and we get a sharper peak showing a less distortion as compared to that of the spherical lenses. Similarly, the weight of the lens was reduced. Like this is a spherical glass high diopter lenses for use for low vision aid person, which is around 14 grams. And if we change from aspheric plastic lens, so it was around 3.9 grams. So there's a reduction in weight by more than 1/3. So leading to definitely less fatigue and can be worn for a longer time to perform their day-to-day activity. So these were the aspheric spectacles which we developed for low vision aids. Further, we are also associated with the diamond turning of the germanium for infrared optics. Now, germanium has wide application in the field of infrared optics, night vision goggles, thermal imaging systems, and high frequency electronics. So, we have been associated with the development of aspheric diffractive optical elements for thermal imaging. So as the conventional lenses are being replaced by the diffractive and aspheric lenses to fulfill the requirement of compact design of the optical system. Nowadays, all the instruments, they are becoming small and miniaturized. So that's why the spherical has switched to aspero-diffractive. So the challenge associated with this is the accurate machine control, proper selection of the diamond tool, and the choice of critical machining parameters, not only to achieve a good surface quality but also a very high diffraction efficiency. So we developed this germanium aspero-diffractive optical element, which was to be used for a thermal camera. This was a project funded by DRDO. So we could achieve a surface roughness of 15 nanometer. This is a profile of the diffractive optical element fabricated, and the step height of the diffractive groove was achieved with the error of 8 nanometers. Since we are talking about nano machining, so error is also in nanometers. And the maximum diffractive efficiency we could achieve was 99.57%. Further, scanning electron microscopy was used to analyze the radial rings on the surface to further analyze the steps and surface quality. So we are also involved into the development of infrared microscopy for hotspot detection in PCBs, printed circuit boards. As we are aware that infrared microscopy is a very useful tool for obtaining the spatially resolved temperature profile of any fully operational microprocessor. So it can be used as a design tool that can greatly aid in a circuit design and optimization of cooling solution. So the challenge here was that we did the machining of zinc selenide material. It is a very preferred material because it can be used in the entire IR range, and also because of its special properties, like it has extremely low bulk optical losses, high resistance to the thermal shock, and stability in all environments. So we did the diamond, we designed as well as developed a plano-convex lens which could be used for infrared microscopy for the detection of the hot spot. So finally a plano-convex lens was fabricated. This is a plano-convex lens of zinc selenide, and further a setup was made by using a 3D printing, which comprises of a smartphone. This is a thermal camera, and a lens is beyond this phone, which is adjusted with the camera of the phone to acquire the images. So we could see that with the help of ZNSE fabricated lenses, the heated object is observed and a significant quality of magnified image with heat signatures is observed using the fabricated lens. Further, we are also associated with the diamond turning of the silicon, which is one of the most difficult material to machine because of its brittleness for the X-rays as well as the IR optics for the focusing of the X-ray beam and guiding the beam to a particular location. So we have optimized and process, and to a very good extent we could achieve a crack-free surface. Now, since I'm talking about nanometric cutting, so the things are not usually visible to us. So in order to analyze the process, we are into molecular dynamics simulation modeling. Like we use this model to basically analyze the nanometric cutting, the changes which are occurring in the material only to a few atomic levels from the surface, and also to understand the material removal mechanism. So this is the model which we developed for this kind of machining, and we could study what are the phase transformation occurring, what are the cutting forces existing, thrust forces, variation of temperature at different points can be studied through this simulation model. Uh, Further, we are also into the we are also studying the subsurface damage detection, and by using the molecular dynamic simulation, like what is the depth. We till now we were associated with only the surface finish, but there are certain cracks which propagates beneath the surface. So measuring those cracks is very difficult, and this is the most essential requirement of any optics, because if cracks are present, then that optics cannot be used at different temperature and pressure conditions. Like we are talking about aircraft, the pressure and temperature conditions are entirely different from the normal conditions. So if any cracks are present, then it will lead to the breakage of optics. So we are also into the determination of subsurface damage by using various modeling techniques and characterization tools. Now, as we all are aware of this pandemic COVID-19, very recently I have been associated with the design and development of safety goggles to combat COVID-19. So we have designed and developed a special kinds of safety goggles, protective eyewear, which are basically made up of sturdy polycarbonate lenses, and they covers the eye, and they can almost cover the entire area, surrounding area, and accommodates the prescription glasses. These are basically indirect venting, and the quality also complies with the this American standard Z87.12010. So we have transferred this technology for the mass production to an industry. These are the mechanical design of the goggles as well as the mold, and these are the developed goggles by us. So these goggles, they meet all the physical as well as the chemical requirement. Like the surface, if we talk about the surface, it is hydrophobic, that is, it is water or blood repellent, so anything will not stick to that surface. And the most important is that it has a luminous transmission greater than 85%, which is the requirement of the doctors to wear these goggles for a longer duration, ranging from 8 to 15 hours. So this has met all the standards, And these now our new frontiers will be in the development of large optics for synchrotron beamline, development of freeform optical elements for display systems, diamond turning of titanium for aerospace, and texturing on diamond tool to improve the machinability. So I will, this was the work which I have been associated. Major R&D facility at CSR comprises of 3D metal printing. We do 3D modeling, engineering analysis, precision force measurements. We have microscopes and X-ray imaging analysis, like we have AFM, confocal microscope, FESCM, Raman microscope, low energy X-ray imaging, and XRD. We also have like chemical particle size spectrometer based analysis, like electrochemical workstation, DLS system, drop shape analyzer, which is basically the contact angle, and fluorescence spectrophotometer, liquid chromatograph, mass spectrophotometer. Now, various facility for optical fabrication, we have SPDT, 2-axis, 3-axis, we have MRF machine, we have fast tool servo, we have a laser interferometer, we have aspheric metrology equipment. For like conventional fabrication, we have sintering and edging. For smaller lenses, we have CMM and polishing machines and other universal test station dry optics. And these are the characterization facilities which we have, like we have a gonio spectrophotometer, laser interferometer, LED characterization, CCI, coherence correlation interferometers. And we also have thermal coating power plants and ion assisted dual beam gun. We have 5-axis grinding, 6-axis polishing. So these are some of the equipments which we have at CSIO. And thank you so much. If you have any questions, you can ask.
Thank you, madam. Thank you for your informative sections.
Thank you, sir.
From participant side, if you are having any doubts, you can unmute your mic and you can ask. You can please unmute your mic and you can ask. Yes, Vemuri. Dr. Vemuri, sir.
Hello.
Hello. Yeah, Praveen, tell me.
Can you explain about MTech and apprentice positions in CSI or CSIO for the BTech and MTech students, who those who are required for them?
Okay. Every year for training or for carrying out MTech and degree and PhD degree?
Both.
Okay, for training, we have like every 6 months, we have a call for MTech as well as BTech training. Online applications are invited. You have to apply online, and on the basis of your application, you are shortlisted and you are intermitted. So there is some fee also for conducting the training. For 6 months. It's around like 5,000 for 2 months and 10,000 for 6 months. And for enrolling in MTech and PhD program, it's like you have to then also every 6 months the for PhD every 6 months the calls are open. You can apply and you will be shortlisted and called for interview. And for MTech it is yearly, not on 6 months basis. So it's mentioned you can get all the details in the CSIO website or in the CSIO websites.
Okay, thanks.
Okay.
Okay. Ravi Kumar, can please carry on. Ravi Kumar. Still any more doubts from the participant side? Please unmute your mic and you can ask.
Hello.
Yeah.
Hello.
Yes, sir.
Are there any job opportunities for BTech graduates? If it is so, what kind of the skill set they should have?
Sorry, can you repeat your question, please?
So, are there any kind of job opportunities for BTech graduates?
Okay.
in electronics? And if it is so, what kind of skill set they should be pursuing?
Immediately for BTech, there is no job opportunities. Like you're asking for permanent job, right?
Yeah, it could be permanent job or any kind of internships. Like in the
Internships are available, as I told earlier also, like every 6 months internship call is there. It is there in the CSI website. You have to apply online, and on the basis of your application, you are shortlisted. It's not like everybody who applies is shortlisted. On the basis of your like academic performance and all, not any written exam is there, but they may be asking for your CV and all. So on the basis of the shortlist, and you can do internship for 6 months if you are shortlisted. But job on BTech basis, presently it is not there. If you can frequently visit, normally job on MTech basis calls are there, not on BTech basis.
okay, ma'am. Thank you.
Still, any more participants? If you are having doubts, you can ask. If no doubts, we'll conclude the section.